Hi, and welcome to H2.5 Rotational Work and Energy. In this lesson, students will be able to analyze the energy of a rotating rigid object. Let's start off by talking about rotational work. If you remember back to Unit 8, Work, Power, and Energy, we talked about work first. So it says a rope wrapped around a wheel is under constant tension F. The rope is pulled out a distance s, the arc length, and the wheel rotates through an angle theta. Okay, so it looks like you're exerting a force over a rotational distance. So we know that work is equal to force times displacement. And the arc length formula tells us that the arc length is equal to r times the angular displacement, which we can plug in for d. So now we have an equation that says that work is equal to Fr theta, and torque is equal to your force times your lever arm. And in this case, the radius is the lever arm. If you look at the diagram, right, this is the perpendicular distance between the line of action and the axis of rotation. So yeah, the lever arm is the radius, and now we could plug that in over there. So we have the rotational work is equal to the torque times the angular displacement, much like how linear work, if you want to think of it like that, is equal to the force times the displacement. So it's just work using rotational variables. So the definition is rotational work is the work done by a torque through an angular distance. What do you think the unit should be for rotational work? Luckily, they're still just joules. You do a lot of work, you could buy a lot of joules. And the formula we just derived, all right, the rotational work is equal to the torque times the angular displacement. Now it's important to note that theta must be in radians. The angular displacement needs to be in radians to use this formula. Where is it located on your reference table? Let's see if we could find it over here. Looks like it's right over here. All right, that's nice. They give that to you. Hey, we're also going to do this one today too. But let's see if we could do an example problem first. This says how much work is done in tightening a bolt with a wrench. The wrench is 0.3 meters long and can be approximated as a long rod. A force of 50 newtons is applied tangentially for a quarter of a turn. If you want, you could pause the video and try this out on your own. Okay, so let's see. We have the force is equal to 50 newtons, and the wrench is 0.3 meters long, and the axis of rotation is here. So that means that the radius is equal to 0.3 meters, or if you want to call it like the lever arm is equal to 0.3 meters. Okay, and they're also telling you some information here, a quarter of a turn. How are we going to handle that? All right, a quarter of a turn, a quarter of a revolution. That's like the angular displacement to me. So 0.25 revolutions or turns. Keep in mind, if we were going to use it's asking for the work, right? So the rotational work. If we want to use our formula, this needs to be in radians. So just a little refresher. All right, write the units on the opposite side, write the units that you want here. How many of one thing equals the other? So 2 times 0.25 is 1/2. So you get pi over 2 radians for a quarter of a turn. Okay? And we could calculate the torque first. All right, 50 times 0.3, and you get the amount of torque, which turns out to be 15 Newton meters, or you could just go straight to your formula. So the rotational work is equal to not the force times the distance, but the torque times the angular displacement. I should have said force times displacement. All right, so the rotational work is equal to, well, we know a formula for the torque. It's the force times the lever arm. So that's for the torque. Don't forget to multiply by the angular displacement as well. So we'll use this formula. We'll plug in 50 newtons. The lever arm is the length of the wrench, 0.3 meters. And we have pi over 2 radians. I'm writing the units in here to show you that it needs to be in radians, because those are, you could think of radians as like unitless. We have a Newton times a meter here, all right? And a Newton meter is equal to a joule. So that's why we need to make sure this is in radians, not revolutions or degrees, okay? So 50 times 0.3 we said was 15. 15 divided by 2 is 7.5. 7.5 times pi gives you about 23.6 joules. If we were going to try to do like sig figs, we could call it 24 joules. Nice. All right, so that's rotational work. Now we could talk about rotational energy, specifically kinetic energy, because it's a type of movement, right? So moving objects have kinetic energy. When an object rotates, each particle of mass is moving about an axis. Therefore, each particle has its kinetic energy that can be summed up. So this is our formula for linear kinetic energy, 1/2 mv squared, and we'll call this the tangential velocity. And in our reference table, we have, this is like the switcheroonie, remember that? How do you go from linear to tangential variables and vice versa? You got to use this. Again, making sure that this is in radians. So we'll plug in our omega. Now we have this. It looks a little messy. I wonder if we could like make it nicer. How are we going to get rid of that R term? And the mass, we don't really talk about mass. We talk about rotational mass, right? Moment of inertia. Do you see some way that we could get the moment of inertia equation in there? Pause the video if you want to think about it. Okay, so it says I is equal to mr squared. That is the moment of inertia for one of those particles, okay? And if you wanted to do, if it's a disc or a hoop or a rod, all right, by using the moment of inertia for the rigid object itself, the formula for it, you're effectively summing up the mass for all that object. So it's basically just saying use the moment of inertia. So, and then we have our nice kinetic energy using rotational variables formula. And you can see the comparison. M turns into I, tangential velocity turns into angular velocity, as you would probably expect. So here's the definition. Rotational kinetic energy is possessed by objects rotating or moving about an axis. The work kinetic energy theorem holds true. If work is added to the system, rotational kinetic energy increases and vice versa. You could do work by taking energy out of the system, negative work, and then you would slow it down. The units, again, joules. Luckily, we don't have to memorize a different thing for that. And we just derived our nice formula. Keep in mind, omega, the angular velocity, needs to be in radians. So where is that formula located? Right over here. We've called it out before, okay? And notice it is, both of these formulas are in the section where we're saying it needs to be in radians. All right, so let's do an example. A helicopter has two blades. Each blade has a mass of 250 kilograms and can be approximated as a thin rod of length 6.7 meters. The blades are rotating at an angular speed of 53 radians per second. That makes me happy. We don't have to worry about changing that out, so that's cool. What is the total moment of inertia of the two blades about the axis of rotation? And then that'll lead us into B, determine the rotational kinetic energy of the spinning blades. If you want, you could pause the video, try it on your own first. So let's write down our given information. If we want, we could do like the mass of the first blade is equal to the mass of the second blade. That's 250 kilograms. And then the length, they're the same length. So that's 6.7 meters. They're telling you the angular velocity is 53 radians per second. And we're going to have to figure out the total moment of inertia for the blades. And they're saying to approximate it as a rod. So it's going to be one of these two. Now this is like its own separate rod. So just focus on this one. The axis of rotation is at the end. All right. So we're going to use this formula. and then we'll basically multiply it by 2. So 1/3 ml squared. I like to write the formula over here. I is equal to 1/3 ml squared. Okay, so let's do the total moment of inertia for the first and second blade. This is going to be 1/3. Really, it's the same variables, ml squared, because 1 is equal to 2. So if you want, you could combine 250 times 6.7 squared. The total moment of inertia is 7,500. It's like 7,481.7 kilogram meters squared. Normally we would round it. I like to keep it long because we're going to do part B and I don't want to round that answer. So it says determine the rotational kinetic energy of the spinning blades. Let me make some room here. All right, so we have the total moment of inertia over there. Now we could treat them separately. We could be like, okay, kind of like we did before, the kinetic energy of the first blade plus the kinetic energy of the second blade. And this is for the total rotational kinetic energy. But why do that? We already know what the total moment of inertia is. So the strategy is going to be the rotational kinetic energy is equal to, remember how it was 1/2 mv squared? Don't forget to put this 1/2 here. I know it's going to be tempting because sometimes you'll even have a 1/2 for the I term, but this is 1/2 times I. Does that make sense? So sometimes you'll plug in 1/2 times 1/2 mr squared or some other fraction, depending on what you're dealing with. Okay, so don't be confused by that. This is the total moment of inertia for both blades that we're going to plug in, and they have the same angular velocity. So 1/2 mv squared becomes 1/2 I omega squared. The total rotational kinetic energy is therefore equal to 1/2 times 7,481.7 times 53 squared. Wow, this is going to be a big number, right? That's a lot of energy that we're talking about. 1.05 times 10 to the 7 joules of energy. What? Is that right? Did we do something wrong? Well, they're helicopter blades, and each one has a mass of 250 kilograms. So a typical person, they say, is about 70 kilograms as a rough estimation. So each blade is very massive, and let's see how fast are these blades spinning. Because it's like, yeah, they're massive, but I mean, this is a huge number. So just so we could see, 53 radians per second, in case you forget how to convert, right? So the radians go on the bottom, so they cancel it. I want to see how many times does it spin in 1 second. Okay, so 53 divided by 2 pi gives you 8.4, which compared to this number doesn't seem like that big, but what are we talking about here? 8.4 revolutions every second. 8 revolutions. These things spin around 8 times in 1 second, and each one has a mass of 250 kilograms. So yeah, just checking for ourselves, this is a big number, but it's a helicopter we're talking about. It takes a lot of energy to generate that much lift to lift up the helicopter. So always a good way to check to make sure your numbers are making sense, for sure. All right, now we could do some fun stuff. So this is total kinetic energy. The total kinetic energy of a rolling object is the sum of the rotational kinetic energy that we just calculated about the center of mass and the translational kinetic energy. Because yeah, it's spinning, it does have this rotational kinetic energy, but don't forget, if it's rolling, that means it's also having some linear kinetic energy here. So there is a velocity, a tangential velocity, and now it's spinning, and we can calculate what that rotational kinetic energy is. When you combine both of those together, that gives you the total kinetic energy. And now we could do super interesting problems with the conservation of energy. Remember, we were like, oh, the total energy is equal to the potential plus the kinetic plus like the internal energy. We won't do one with friction, right? And then if we, for this class, we've learned about two types of potential energy. I call it GPE for gravitational potential energy plus EPE for elastic potential energy. Plus, now we're going to call this the tangential or the translational kinetic energy plus the rotational kinetic energy. And so there's a lot of different types of energy beyond these ones that we are calculating in this class. Um, but yeah, so we could do some really interesting problems now, including, and we're going to have like the moment of inertia in there. We're going to have, make sure we're in radians. It's going to be a lot of fun. So see if you could try this one. It says a hoop and a cylinder, so classic example from the previous lesson, are released from rest from the top of a 1 meter tall hill. They're telling you what the height of the hill is. The radius of the hoop and the cylinder are both 0.1 meters, good to know. The mass of the hoop and the cylinder are both 1 kilogram, also good to know. So we could figure out what that rotational mass is, the moment of inertia. Part A says, which reaches the ground first? Calculate the final translational velocity. Okay, we have a lot of tools in our tool belt now. How are we going to do that? Part B says to calculate and compare the translational and the rotational kinetic energy for each object, just to see. And then part C says, compare the total kinetic energy of the hoop to the cylinder. So individually for each one, I wonder maybe that it's going to have more rotational kinetic energy than translational. What do you think? I don't know. And then we're going to add them together for each one and say, okay, are the kinetic energies, the total kinetic energies, the same? Are they different for the hoop and the cylinder at the bottom of the hill? What do you think? What would you expect that comparison to look like? Okay. So if you want, you could try it on your own first. Let's see what we got. If you're not trying it on your own or you tried it and you got stuck, the first hint I'll give you is we're going to be doing the conservation of energy. So this is your hint, okay? See if you could figure it out now. All right, but before we do that, let's write down some information. So we know that the height of the hill is 1 meter. That's good. We know that the radiuses are the same. So R1 is equal to R2 is equal to what it was 0.1 meters. The mass. Mr. Nangle, why are you making capitals? Oh, because I'm going to use the moment of inertia formulas that look like this eventually. Okay, and they're all capitals in these. So they also tell you, what do they tell you? It's a hoop and a cylinder. So we know for a hoop, the moment of inertia is mr squared. And for the cylinder, it's 1/2 mr squared. Okay. The problem tells you they are released from rest. So VI is equal to 0, but also omega is equal to 0. So does this mean that we're going to have to do like kinematic equations and like what is the torque? How would you find the torque? And Newton's second law? Torque is equal to I alpha? I wonder if there's an easier way. Yeah, let's not deal with that. Let's look at this from the conservation of energy standpoint. I think we have enough information now. So we want to know for the hoop, what is the final velocity? Well, yeah, not angular velocity. Let's figure out the final velocity of the hoop and the final velocity of the cylinder. Okay. Let's start by talking about the hoop. And I'm not going to use the subscripts because to denote between, and I even messed it up over here. These should be like hoop and cylinder. Let's just start by doing the hoop so we don't have to worry about those subscripts. So we said the total energy in the beginning is equal to the total energy at the end. That still holds true. In the beginning, it is important to know that you don't have any initial velocity there. So there's no kinetic energy in the beginning. You're not compressing a spring or anything, but you are a height above the ground. So initially, all of that energy is gravitational potential energy. And then at the bottom of the hill, you're on the bottom. So there's no more potential energy. There is kinetic energy. Now it is moving linearly. It's translating across. And it is also rotating. So this is the rotational kinetic energy. So we know mgh, okay? We know 1/2 mv squared. This is really the final velocity. I'm going to just call it v for now because I don't want to get confused with all the subscripts. Plus 1/2 I omega final squared. Okay? Well, this isn't really helping us that much. I know I wanted to know what the final velocity is, but this is kind of messing me up over here. So first situation is, well, first let's get rid of this omega. Okay? We know that this is the switcheroonie. So omega is equal to V over R. Okay? So we're going to switch that out. V over R. And then we know this is a hoop. So in my next line, I'm going to do mgh is equal to 1/2 mv squared plus 1/2 I for the hoop is mr squared. And then V over R squared becomes V squared over R squared. And now we're looking pretty happy. Do you see where we're going to go with this? The R squared cancels out with this R squared. And divide everything by M. The M's cancel out. Whoa, that's nice. So GH is equal to 1/2 V squared plus 1/2 V squared. What? Yeah. Take a look. So 1/2 V squared plus 1/2 V squared is just V squared. Take the square root is equal to square root of GH. What? The final velocity is the square root of GH. And now keep in mind, this worked out because this is I is equal to mr squared. All right, so that's why we got the 1/2 over here. It just stayed as 1/2. All right, and that worked out to a whole V squared. That's nice. It's not always going to be like that. In this case, it was nice. And then, yeah, wow. So this is equal to the square root of 9.8. How high is that hill? Just 1. Oh, so it's the square root of 9.8 in this case. And you get 3.13 meters per second. That's the final velocity of the hoop. If the final velocity of the cylinder is greater, we know the cylinder reached the ground first. Do you remember which one did reach the ground when we were talking about the moment of inertia? Let's see. So for the cylinder, see if you could do the cylinder one now. I'm going to skip ahead a little bit, but you pause the video and I'll stop when it becomes different because it's mostly the same. Okay, so this is still the same. We could still do the switcheroonie where this is V over R. The thing that's different is I. So remember, I was saying, like, don't get confused with this 1/2. That 1/2 stays there. This is 1/2 times I. And for the cylinder, I is equal to 1/2 mr squared. So we're going to plug in 1/2 mr squared. That is I. So don't get confused by that. That's okay. That's good. That's what you want for the cylinder. Times V over R squared when you're doing the kinetic energy, or rotational kinetic energy, 1/2 I omega squared. All right. Now you could see it's going to be a little bit different. We are going to do the trick where we square what's inside those parentheses there, and that allows us to cross off r squared and r squared. You can divide the whole equation by m. Those all cancel out. And what are we left with? GH is equal to 1/2 v squared again, plus 1/2 times 1/2 times v squared. So 1/2 times 1/2 is 1/4 where I come from, and this is v squared. So now it's not going to work out to be like, oh, 1/2 plus 1/2, that's 1. All right, it's a little bit different because we're talking about a cylinder. 1/2 plus 1/4 is 3/4. And then to get rid of that, right, how do you do times the reciprocal to both sides? Okay, so those will cancel out, 3, 3, 4, 4. So v is equal to the square root of 4/3 GH, which is going to give us a slightly higher velocity than before, because this was 1 GH, this is now 4/3 GH. And you get about 3.6 meters per second. Okay, so yeah, the cylinder is traveling faster. It reaches the ground first. Part B, okay, so we now know, oh yeah, this was for the final velocity of the cylinder, and this is for the hoop over here. So we know those. Now I'm debating on whether or not to, maybe I should just erase this portion of it and plug in the velocity over here and show it like in the equation, but I think that might be a little bit too messy on the screen. But you could think of it that way. We're going to do part B where we compare the translational kinetic energy and the rotational kinetic energy for the hoop and then for the cylinder. So I'm just going to make some room here. And then maybe I'll like color coordinate things. And now I'll use the subscripts for the hoop and the cylinder. So the kinetic energy for the hoop, the linear or the translational looks like this. You get about 4.898, so 4.9 joules of translational kinetic energy. And then for the rotational, we're going to have to plug in for I, and we didn't calculate the final angular velocity, so we'll use the switcheroonie again. And actually, when you simplify this equation a little bit, these r squared terms cancel out, and you're left with something that looks like 1/2. Looks like your old formula, 1/2 mv squared. So it's going to be the same thing. But that rotational kinetic energy changes depending on what your moment of inertia is. So for the hoop, the moment of inertia is pretty straightforward. It changes a little bit with the cylinder because you have that 1/2 in there as well. So for now, it says calculate and compare for each object. For the hoop, they're the same. For the cylinder, you get a translational kinetic energy of 6.48 joules, which is greater than the hoop's translational kinetic energy. And when you're calculating the rotational kinetic energy, again, when you're plugging in for I, it's 1/2 mr squared. That's I. And then we're going to do divided by v over r squared. So yet you do get some canceling happening. You do get a similar looking equation. This is 1/4 mv squared, because again, the moment of inertia is different now. So you get 3.24 joules. That's the rotational kinetic energy. So if we were going to compare, the cylinder has more translational kinetic energy than it does rotational kinetic energy. The hoop had the same amount. Part C says compare the total. So for the hoop, you have a total kinetic energy of 9.8 joules. That number seems familiar. And then for the cylinder, you get almost the same. It's like 9.72 something. So it's about 9.8. If I was going to be like 9.72, why is it a little bit different? We rounded this. So for my final point here, let's just say it's 9.8 joules because we rounded, right? So it is 9.8 joules, the total kinetic energy, if we didn't round all our stuff. That's kind of crazy. They have the same total kinetic energy of 9.8 joules. Where did they get that energy from? This total kinetic energy is equal to the gravitational potential energy. What? mgh, the mass, is 1 kilogram times 9.8 times 1 meter in the air for both of them. So the conservation of energy holds true. We just have some more fun with our rotational kinetic energy happenings. Great. Well, that's about it. Thanks for watching and have a great day.